Evening, everybody. Can you hear me
Good evening, sir.
Hello, good evening.
okay? Evening.
Good evening.
Good thing that I realized that I was muted. uh, I was muted on my headset. Right.
I think it's the most repeated phrase during COVID times.
Or
Sorry, I was muted.
or I could not hear you disconnected.
Yeah.
Right. Okay. So first things first. Welcome. We're going to start off today's lesson by first and foremost taking a look at your assignment. I would like to ask you to check whether or not you can actually see the assignment on Moodle. Could you please double check that, please?
Yeah, I actually saw that over the weekend.
Okay, good. All right. Because I wanted to make sure that all the settings were in place so that you'll actually be able to see it properly. Okay. If you do have issues in seeing it, please do feel free to message me. All right. Let's go over this assignment so that you understand what is basically being asked of you. All right. The assignment is centered around um, uh, your exploration, if you will, of the ping utility. Okay, so essentially the aim is for you to learn about the ping utility and conduct a simple experiment regarding this ping utility. Essentially, the deadline for this assignment is going to be Friday, the 18th of February. Okay, you have a good 3 weeks, obviously including this week, um, uh, to get it done. It's a relatively simple assignment overall. Okay, so essentially you're going to be learning about the ping utility and conduct some small experiments and obviously conduct a little bit of a research upon this particular topic. Obviously, make sure that everything is written in acceptable English. That you write your report in and save it as a PDF format and upload it onto the Moodle link that is available for you. All right, for your submission. All right. As I said, this assignment includes a little bit of research, so it makes sense that you include adequate citation. All right, kind of like the way that I had shown you for the very first assignment. Note that you do have access um, to um, uh, to resources on Moodle as to how to cite. All right. If I'm not mistaken, it is under the cap of what was it called? Yeah, that's from the no, I have to double check because I forgot the name exactly. So uh, yes, that's right. That's right. The personal development program. So please take a look at um, uh, the how-to guides that are actually presented over there. Okay, so that you do not lose any marks which are referenced, which are reserved for referencing. Okay. I was a bit confused as to its name because it has undergone a number of different name changes along the years. So I was I was not sure as to what it was actually called. But do please make sure that you make use of adequate citation techniques, all right, in your work, all right. This year, we are trying to train you in order to become better at it. All right. However, as you progress in your studies, it becomes more and more and more important. Okay, because obviously you don't want to plagiarize anybody's work. All right, and if we do get suspicion of any form of plagiarism, we reserve the right in order to conduct an interview or meeting in order for you to explain your work. All right. Obviously, plagiarism is not acceptable. All right. When we talk about plagiarism, we're talking about copying and pasting other people's works. Just to let you know, each and every work that you have submitted is actually being checked. All right. We actually pass it. When I correct your assignments, I actually pass it through a system that checks for the amount of plagiarism in that, and if it goes over above a particular threshold, um, uh, then we might start procedures with regards to plagiarism, depending on a case by case basis, obviously, because it depends on what is plagiarized to a certain extent. All right. Obviously, automated systems may pick up certain things which are considered as being plagiarized, which are not really plagiarism. So you have to filter them out, but we vet them. All right. So please be aware of that. Okay. Obviously, make use of the personal development program, as Alex pointed out earlier, to help and see how you should um, be referencing your works. Okay, so let's get down to the nitty gritty of the assignment itself. So, the assignment, as I said, is about you being a bit more aware about an important tool in networking, and that is the ping utility. All right, the ping utility is found in the Internet Protocol, or IP, which primarily aids administrators measure the time messages take to reach their destination and come back. All right. So for the first part of the coursework, you are going to do a little bit of background research on this utility and become a little bit more familiar with it and how to conduct this. All right, so you need to conduct research into the ping utility itself and provide some form of background upon what the protocol, what it is, and what protocol or protocols it is attributed to. All right, and you should write a report around 300 words. That's about a page worth of an essay, if you will. All right, obviously including proper citation techniques for any statements or facts that you list down. All right, so if you say that the ping utility is something something something, all right, and you read that from facts.com, then make sure that you cite facts.com, because you want to make sure that what you're saying is properly sourced. Notice that if a similar fact has been said in multiple sources, then it gives even more credence to that source. All right? Think about it. If only one person basically is stating something and it's not really backed up by anybody else, then you probably can think that it is quite a weak argument. Whereas if more people are citing it, the better. Now, obviously, when we say by more people citing it, we're talking about more academic sources. All right, it's not good enough to say because Charlie from the other side of the island said so, therefore it must be true, and or because Charlie and Bobby said something, therefore it must be true. It obviously has to be from credible sources, okay, and not sources like Facebook or Wikipedia or whatever. All right, we're talking about ideally, all right, sources which have which are academic in their nature. You might want to make use of instead of the simple google.com, you might want to make use of Google Scholar, for example, in order to help you out with that. Okay. Um, then you need, all right, so along with that 300 words, you need to explain how it can be used, all right, including examples of syntax and parameters. Now, obviously, different people might be using different types of systems, all right, so the way that you might make use of the ping utility on a Windows system might be slightly different from that of a Mac system or whatever. All right. In that case, you need to showcase the syntax that you use for each and every for each system that you have for the system that you have. All right. But you need to also back that up with um, um, with screenshots. All right. And obviously, make sure to cite the syntax that you're going to be using, all right, in order to put forward this command, this ping command, and reference them as well. Okay. So far, so good. Any questions with this?
No, clear up till
Thank
now.
you.
Thank you from me.
All right. So that's the first part. The second part, okay, is basically a continuation, all right? Essentially, you're going to conduct a simple experiment where you're going to identify 3 locations from different continents, all right? So we're talking Africa, Europe, Asia, for example, or Africa, America, and Asia, whatever, all right? And you're going to basically find 3 websites, all right? Each one of these websites on different or hosted on different servers on different continents, all right? And you're going to, first and foremost, you need to check the location of that website, all right, to make sure that the locations are, in fact, on different continents. And you can do that by also indicating your proof of geographic location using screenshots as well, if needs be. All right. Then, once you have found these websites, all right, you are going to perform the ping utility, all right, and study how long it takes packets to arrive those particular destinations. All right. Then you're going to need to find an online distance calculator, all right, to measure the geographic distance, all right, between your location and these 3 locations that you've chosen. Okay, again, including screenshots. Just saying Google Maps is one of them, or Google Earth is one of them. But anyway, find the distance calculator of your choice. All right. And then on your results of your experiment. Essentially, in your discussion, you need to compare, all right, between the geographic distance and the average time that it has taken each and every one of these packets to reach your locations, all right, for these websites. Now, fair warning, sometimes due to security threats and several and other things, several servers might not accept the ping utility. So it might require a little bit of trial and error in order for you to find those 3 different websites which you are going to be able to conduct your experiment. Okay? Are there any questions with regards to this?
None. No, I'm fine.
Okay. So finally, what you need to do is you need to make a report, all right, on your findings. So you need to submit a PDF document It needs to include the title page, all right? Use the template that we provide. It should also include the table of contents. Ideally, also the table of contents will also include page numbers, all right? Sometimes some people didn't actually include that in past assignments, but again, let's learn from past mistakes, all right? You need to provide an introduction whereby you're going to give a brief background of what somebody's actually going to find further down the line in your report. All right. Then you're going to need to have your answer for part A. All right. So the background research on the syntax that you need to do, including valid academic citations. Part B, you need to provide your work regarding your experiment, all right, including screenshots, and obviously make sure to explain all the tools and links that you use in order to conduct this experiment. Okay, so if you use a particular service, all right, or a particular tool that you found online, make sure that you explain exactly what you did and how you did it. All right, and finally, include a conclusion to briefly outline what you've learned. And what you did within your assignment, all right, to round off your work. Notice that as a general trend, I tended to see that a lot of students either focused on answering one part of this question or the other. All right, they either answered what they learned from the from the assignment and didn't sort of like wrap up what they did, or as they just talked about what they did and then didn't explain what they learned. It's important that you do both here, all right? So please do take your time in order to answer this well, all right? Usually it's not a couple of sentences, you know, I'm looking for a good 2 paragraph here, okay? Obviously, follow these guidelines in order to help you uh, provide a more presentable report. All right, make sure that you use subheadings. All right, and avoid having huge chunks or huge um, blocks of text. All right. Because they make it not as easy to read. All right, start each new section on a new page. All right, whenever you use diagrams, explain them. All right, then don't just put diagrams and just leave them there floating in the ether. All right, use the template that we provide, and obviously for all information, including diagrams, you need to reference them. All right, and obviously make sure that you use correct spelling and grammar checks. Okay? That's essentially it, and this is basically how the marks are actually going to be broken down. So you have 5 marks for your introduction, 20 marks for part A, 60 marks for part B, and 5 marks respectively for your conclusion, presentation, and references. Any questions with regards to the assignment overall?
So the final word count has to be around 300 or a single page anyway for all the parts.
For part A. Part
For part
A.
A. Okay.
Part A. So essentially, this discussion of the ping utility, all right, that should amount to 300 words. This
Okay.
part here, all right, part A1 actually, okay. Then part A2, you should provide
The top. Mhm.
the syntax that you're going to be using, all right, and then part B is your experiment. Okay.
Okay, good.
Any other questions? All right. Doesn't seem like you do. Obviously, if you do have any questions that you would like to ask me, all right. Obviously, feel free to do so. All right. Do not leave it for the very last minute. If needs be, we'll also meet up before the lesson if needs be to talk it over. So don't hesitate to message me. Those of you who have actually messaged me in the past know that I tend to answer as soon as I can, at least. All right. If you prefer using Moodle, you can use Moodle. If you'd like to use Discord. I am flexible. All right. So that is your assignment. Okay. We're now going to continue with the the topic that we were covering in our last lesson. Essentially, we finished off by talking about the difference between switching types, all right, whereby we said we have circuit switching is essentially when a physical circuit is actually set up, all right, for the duration of a call, all right, or the duration of a communication between two nodes, all right, and the entire bandwidth of that circuit is taken up by that particular communication. We also talked about message switching, which essentially does not necessarily have a specific circuit set up for that communication. However, a message in its entirety is actually sent from sender to receiver in its entirety via different nodes. All right, but notice the message remains um, in its entirety, all right, along the way. Whereas packet switching takes that message, breaks it up into smaller segments, and sends each packet, all right, through the network. Again, it can possibly use several different paths in order to reach the destination. However, by sending these different packets, all right, and by each packet possibly taking a different route, all right, it could well be that several packets might arrive in a different sequence, all right, than that being sent by the sender. So the receiver would need to reorganize, all right, these packets together in order to reformulate essentially what the original message was. Okay, so those are the different types of switching that happens within a network. All right, now when we talk about networks, again, we tend to define networks. All right, in using certain terminology in order to help us understand what we're actually talking about. Usually, when we just use the term network, essentially what we're talking about is a number of different systems which are interconnected, all right, in order to share information or resources. Notice that I haven't actually used the term. The term computer or the term any um, any when we have a number of different systems connected to each other and they are actually communicating information, that technically speaking is a network. All right, like the radio network or the television network. A computer network, on the other hand, is a network that is comprised of computer systems. All right, so you have computer systems, terminals, servers, and other components which aid in the communication between different computers. Hosts, on the other hand, are
Nisma dal
computers.
il-pajla.
Excuse me.
Sorry, sir, because I'm in the office and there's still some people around. Sorry.
All right, I thought you had asked me a question or something.
No.
Okay. Yes, and finally, a host is essentially a computer which allows one to run user end applications. Essentially, you connect to a host all right, in order to access certain services provided by that host. Okay, so these are some definitions that we use when we talk about networks. In fact, an internet, all right, is essentially an interconnection of different networks. If you think about it, all right, we are currently speaking over the internet because packets that are leaving my computer are traveling through my network, all right, through my firewall, through my ISP, to your ISPs, and back through your individual networks and directly into your own computers at this point in time in order to decipher what I'm actually talking about. All right. In fact, different gateways allow us to translate, all right, the message that is actually being sent over different protocols. So, for instance, if I am currently, I am currently talking to you over a wired network, all right, and somebody is, and I have an Ethernet cable, all right, for example, that is in turn being fed into my modem, which is using a coaxial cable. So there is a gateway there. That coaxial cable might be transformed into a signal over a fiber optic cable. So another gateway there, and so on and so forth. So for every translation, if you will, all right, between uh, different different types of communication and types of connections made between one system and the next, you would have different gateways, and they might also make use of different protocols as to how to change the communication or change the way that communication actually happens between one system and the next. All right. The complexity of the internet is very hard to fathom. All right, but essentially, if you think about the internet as being just a collection of networks connected to each other, it makes it a whole lot easier in order to wrap your head around what the internet essentially is. All right. Networks can also be defined or can have defined within them what are known as subnets, all right, which is basically a portion of the network which is sort of like secluded for itself. All right, I actually have a subnet set up over here, so that whenever I need to to host or connect or give remote access to a computer connected on that network to somebody else. All right. They would be able to do so without actually having any knowledge of the rest of my home network at home. So subnets actually provide um, provide a necessary tool, all right, in order to help us split up and make more optimal use of our networks, and also improve security, even with respect to to the networks that you have in place, right? Um, so that way, someone at your house would be able to use your Wi-Fi, but not your LAN. That's well, technically speaking, a guest Wi-Fi network is also a subnet to a certain extent, because they wouldn't actually be able to have access to other devices on the network. They will just have direct access to the internet and nothing else. So yes, a guest network can have that. I just have another one which allows me to use a wired connection for a more stable connection. Yes. We're actually going to be talking about the internet, about internet. So we'll get to that further down the line, if you don't mind. Okay. Any other questions? Okay.
No, thank you, sir.
All right. So, again, when we talk about networks, sometimes in order to understand what kind of network we're also talking about, we tend to describe networks in terms of also their coverage, all right, or how big the network actually happens to be, all right, and usually we use terms such as wide area network or WAN or metropolitan area network, all right, such as MAN or local area network, LAN, and personal area network, in order to understand what size of network we're really talking about, all right? Now, different network coverages tend to tends to overlap in terms of their size. So, for example, when we talk about a wide area network, we're talking about from large cities to countries. All right, a metropolitan area network could be anything from a few city blocks to an entire city. All right, a local area network could be anything from a home network to an office network to a building network. All right. So technically speaking, a local area network size can actually vary quite a lot, as can a metropolitan area network, as can a wide area network. The only one which is slightly smaller, all right, is the personal area network, which is a network in the zone, all right, or close to the an individual person. All right. Usually, a personal area network is one in which we're talking about devices connected to each other, which are in reach of an individual person. Usually, we're talking about a Bluetooth network. All right. So, for example, your phone connected to your watch, connected to your car. All right. Connected to Bluetooth earpieces, that kind of network. Okay, that is what is known as a personal area network. Yes, a mobile hotspot could also fall under the personal area network for the same reason that the power of the mobile device might not be that powerful, and therefore the distance that you would have access to that mobile hotspot would be somewhat limited as well. Okay, so yes, as you can see, there is quite a little bit of an overlap in terms uh, of these terms. Sometimes they are also used interchangeably. Uh, However, so, for example, people might refer to a metropolitan area network as being a WAN, for example, and a personal area network being a personal LAN. All right, so essentially, it's still it is you can understand where somebody's where these can actually overlap with each other. In fact, within some of these categories, you also have, for example, like home area network, so HAN, all right, which is smaller than the maximum LAN size, if you will. They're just different categories that allow us to understand the scale of the infrastructure involved. Now, obviously, not every LAN is the same. Not every home area network is the same. Some home area networks are downright simple, all right, and others are much more complex by design. No two networks are really the same. You can ask my electrician that the amount of cables that I actually needed to pass around this place before I moved in was quite substantial. So yes, he said that he has wired offices with less data cables going around those offices than I have in this place, and it's not as if I live with 16 people here or something of the sort. It's just me and my wife. So, yeah. So there are networks and there are networks. Right. When we talk about larger networks, especially networks that might span campuses, for example, all right? So take, for instance, universities and something of the sort, okay? Sometimes also known as campus area networks or CANs. They tend to need what is known as a network hierarchy. Essentially, a network hierarchy is one which allows um, different um, different structures to be put in place in order to help connectivity around the entire campus. All right. So you have a number of different levels. At the base level, all right, you have what is known as the access network. The access network is basically the network that the end user is eventually going to access the network from. Okay, so if we take, for instance, St. Martin's as an example, whenever you log in to the St. Martin's Wi-Fi, for example, on your laptops, on your phones, all right, essentially what you're really making use of is this access network. It's what gives you the access to the internet that you need, okay? The access network, in turn, is connected to what is known as the distribution network. Now, the distribution network essentially is the network, which is predominantly um, um, predominantly tasked in making sure that the security, all right, of the network is maintained, as well as the quality of service is maintained. Okay, so essentially, what the distribution network does is that it tends to provide more resources to, for example, certain nodes that require higher usage of the network. So they tend to distribute the load across the network. They also tend to make sure that the network or the access that is actually happening across the network is following the protocols that have been set up, all right, by the network administrator, and they in turn are then connected to the core network. Now, the core network essentially is the network that allows, okay, communication to happen across different buildings usually. All right. So if we're talking about a university campus, all right, the different buildings are in themselves sort of connected using a core network. The idea is to be able to have people communicating with from one computer to another computer, which might not necessarily be in the same building. All right, they need to make use of that core network. All right, that core network then allows the distribution networks to connect to that core network. The distribution networks, in turn, all right, are, as I said, what distributes the access throughout the building, for example. So you might have different distribution networks per building, all right, and then you would have your access networks, all right, for your individual lands. So essentially, if we had to look at a little bit at the diagram, All right. Let's say we have 3 buildings. So we have building 1 here, building 2, and building 3. These 3 buildings have the core network between them. All right. And then each individual building will have their own distributed network. All right. So they might allow us to distribute. So you might have one distribution for each floor, for example. All right. And each floor might have a number of different LANs. So you might have a number of different local area networks for, let's say, um, each computer lab, for example. So you'll have, let's say that each floor has 3 computer labs. So you might have an access or network for one computer lab, another one for a second computer lab, and another one for the third computer lab. Those in turn are then connected to yet another network, being your distribution, network. All right, which in turn are connected to your core network. Okay, is this understood?
Yes, sir.
Okay.
Sir, from my end, can you please re-explain the distributed network, please?
So, let me share a better diagram, if you will. So, this is an example
Thank you.
of a distributed network. So, at the top here, you'd have this is obviously a more sophisticated, shall we say, quasi full mesh computer network. The top
Mhm.
here, this is your core network. All right. So imagine this is in building 1. This would be in building 2. All right.
Okay.
As will be these. All right. Building 1 and building 2. All right. Again, this is a simplified diagram in order for us to be able to understand what's going on. Okay. So imagine, if you will. All right. Actually, I think I better draw it out. So give me a moment. Let me.
From my end, I'm understanding this way because I can relate a bit with our office's network.
So actually let me draw it out.
You don't want to go through the trouble, but
Let me draw it out.
okay.
So that it's a bit. Whoop. Don't tell me that this is.
Hmm.
It's playing about. Yes. Give me a moment.
There is no noise right now, sir.
What do you mean?
From coming from my end.
No.
Okay. Alright. Thank you.
No. I'm just making sure that. The problem is that this particular pen, I would need to restart the computer, unfortunately, because I played around so many times with the connections that it has. It's mana.
Don't worry, sir. I was from my end. I was understanding at least from this diagram.
So, mana. What I was trying to say is that usually when you have when you have larger, more complicated systems, all right, what you would end up having is a network that connects different buildings together. Okay, that would be your core network. All right. So essentially, what we're saying is building A is connected to building B, building C. All right. Now, in each building, all right, you might have a number of different networks, all right, which are going to be used for different things. All right. Let's say you have a building which is going to have a number of different floors, and on each floor you're going to have a number of different types of offices or laboratories or whatever, sometimes it's best to understand it in terms of a university, because you can obviously imagine the type of scale that is actually needed. Yes. Or so essentially what you would have is the the um, uh, the access layer will give sorry
The
the
core.
core the core will give will give service, if you will, all right, to the distribution network. So the distribution network's job, all right, is sort of like to control what's going on inside the building. Okay.
Okay.
So essentially, it makes sure that there is a quality of service provided to each and every other network that might be connected to it. Over here, we're talking about the access networks. All right, these are different lands that are in turn connected to it. Okay. Now, in this particular diagram over here, there is an element of redundancy. All
Of
right.
course, yes.
So if one node breaks, then you have the other one, or if there's a high load on one component, then you can make use of the services of another node. All
Mm-hmm.
right. So this is in fact known as a
Planning
as
trees.
this is essentially something that has a better quality of service. Essentially, it is it provides um, uh, it provides a redundant service, so if, for example, this node within the core network is down, then you can
Mm-hmm.
use this node, all right, in order to communicate with the other core nodes. All
Mm-hmm.
right, that's essentially the idea. Similarly, you would have um, uh, two distributors. All right, essentially, it also allows one to be able to um, 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 uh, distributes traffic more adequately across the network as well. All right. So let's say, for instance, that this particular access node is demanding high volumes of traffic. All right. Then instead of overloading one distributor node and one core node, it can sort of like split those requests over multiple distribution nodes and
Mm-hmm.
in turn multiple access nodes, which in turn could then um,
And then the access nodes. Of course,
yes,
those are the nodes to which clients connect to.
yes, essentially.
Okay. All right. All
All
right.
right,
I understand. Okay.
that's essentially the idea behind it. Okay.
Okay.
Now,
Thank
obviously,
you.
when it comes to larger networks, where communication is very, very much important, then having an element of redundancy would be important. Okay. Um, uh, Essentially, if you have absolutely no redundancy, then the problem is that once one node falls, then
Hello?
everything else will fall. Okay, that's the
Think
idea. Can you hear me?
I can't hear you. anymore from my end, sir. I don't know if it's just from my end.
I can hear you.
I can hear them.
Yeah, I think it's just from my end.
Um, can you hear me now, Floyd?
Yeah, I just disconnected and reconnected. I can hear you. Sorry.
All right. Okay. So essentially, the idea is in order to ensure quality of service and to ensure that that you actually have um, a connection. All right, which is a bit more robust. Essentially, that's the idea. Okay. Okay. So, obviously, when it comes to networks, there are different ways of how one can actually put together a network. Okay. Essentially, the way that we put together a network is known as a topology. A topology is essentially the way that different computers are actually connected together. All right. Now, we tend to classify networks based upon these topologies because different topologies, okay, have different features, all right, which results to pros and cons of that particular network. Okay. Now, there are topologies which do not necessarily make up only or do not make use of only one type of topology that we're going to be talking about here. All right. There are also what are known as hybrid networks, essentially networks which are composed of two or more of these basic topologies. Okay. So let's go over the different types of topologies and try to understand essentially, all right, what kind of what kind of topologies exist, all right, and what are the pros and cons of these different topologies. So let's talk about the very first one, which is the bus topology. Okay. What I am actually going to do, all right, so that you'll also be able to understand these topologies a bit better, is I'm going to show them to you like so. All right. So first and foremost, I'm going to share you with the link. All right, so that you will be able to find it at a later stage as well. All right. The first topology that we're going to be talking about is the bus topology. Okay, so the bus topology essentially includes what is known as a backbone. All right, essentially it is a central wire. All right, which has a terminator on either end. Okay, of that wire. Okay, and you have computers which are then connected to that backbone directly. All right, and it is a very, very, very simple form of network. Okay, essentially, each computer will have its own number. All right, and when a computer, let's say they are numbered 1, 2, 3, 4, 5. Let's say that computer 1 wants to send a packet or send a message to computer 5. Essentially, the computer over here will send the message. All right, and the message will reside on this data line. All right, these computers will sort of like be listening in onto any data that is coming or any packets that are coming in on this data line. All right, and um, essentially they would check to see whether or not that packet is meant for them. If it's meant for them, then they will read that packet and understand what that message is. All right, since this message is being sent to computer number 5, then essentially these three computers here will ignore the message and it will be read by computer number 5. Okay? Now, the problem with this particular form of network, well, first and foremost, this particular form of network is very, 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 very cheap and very easy to set up. Okay, because essentially what you need is one central backbone, and you just need to plug in to that computer, to that particular network. However, the problem with this network is that the bus itself, all right, can be susceptible to a number of collisions in the form of multiple messages being actually sent across that network. So essentially, what that means is that if there is a high volume of data packets that are actually being sent across this network, then essentially what you would have is packets colliding with each other, and they won't actually be arriving at their destination. Okay. You might be asking, what happens if, for example, this computer disconnects from the server, or from the or rather from the network? Then essentially, when this message is sent on this line, all right, it would probably have what is known as a time to live function. All right, so the packet will remain existent for a period of time. All right, once that time is up, then essentially it would be dumped. All right, by the terminators. All right, essentially it will be drained and ignored. Okay, is this clear? Yes, yes, yes. No, no, there's no server that controls them. Essentially, it's like imagine you have a imagine you have a conveyor belt, if you will.
Yes. Okay.
Okay. Um, uh, have you ever been to a sushi restaurant? Let's put it that way. Have you the ones
Yes.
that have a conveyor belt? Essentially,
Okay.
if you want to pick up something from that conveyor belt, you just pick it up, and essentially what is happening. Imagine this as being a conveyor belt. All right. Usually, data either flows in one direction or the other direction. It depends on how this is actually set up. Okay.
Okay.
Um, um, what would happen is that one computer would put data onto the conveyor belt. All right, it will move along. All right, and the computer that is required to read it will pick it up from the conveyor belt. Essentially, that's the way that it would work.
Okay.
All right. Obviously, the problem with something of the sort is that essentially the data that is being placed onto the network, technically speaking, is accessible to all.
Yeah.
It's only from the sheer goodwill of the other computers on that network that they won't pick up that data. However, with software, you could have a system where you'd be able to intercept that message. And in fact, from those most heist movies that you watch, that actually show you that they're actually plugging into the network and they're actually reading everything that's going on the network, probably would be plugging into something of the sort, if you know what I mean. All right.
Yes. Okay.
Obviously,
Okay.
it's more simplified in the movies, to make it a bit more interesting, to seem as though they're actually getting. But that's essentially the way
Okay.
that.
A bit more exaggerated in the movies.
Yes, it is a bit. Obviously, if you've ever noticed people in movies when they're typing, they rarely use the space bar.
Yeah.
That really pisses me off. But anyway, uh, but yes, that can happen. All right, so it can
Okay.
be susceptible to those kinds of attacks. You know, basically they're known as man-in-the-middle attacks. Okay. Um, uh, but obviously you need to plug into that actual network. You know, it's not done wirelessly. This is a wired network. You know, so in that sense, it could be a bit secure in the sense that it's wired. Okay. Um, so that's the first network. The second
Okay.
network that we're
Thanks a
going to
lot.
be. Thank you. The second network that we're going to be talking about. Whoopsie daisy. The hell. The second network that I would like to talk about is this ring topology network. So essentially, the ring topology network has computers sort of like connected the computers to the left and to the right of them. Okay, so each computer is connected to a computer to the left and then another computer to the right, in such a way that they form a ring. All right. Now, the cool thing about this um, topology is that essentially what it could what it allows is well, sorry, it does not require a a backbone to be placed. All right, because obviously expansion of the backbone can be a bit problematic if you think about it. All right. However, this kind of topology would then, if is relatively simpler for the simple reason that each computer is then connected to its neighbors, all right, one to the left and one to the right, if you will. So essentially, um, a message that is sent from this computer, say, to this computer, will go around, all right. Um, the packet will go through this computer will notice it's not for him, and it will pass on the message to the next computer. If that message is for that particular computer, then the message is read. All right. Now the problem with this kind of topology is that again, when it comes to high data transfer, um, uh, what what would happen is that you would actually be bottlenecked, all right, in sending these messages across. Because essentially, what happens is that each computer will be given, or each node on the network would actually be given um, a time slice for them to actually be to actually communicate with the next computer, all right, if you will. All right, so you are essentially, it's known as a token ring network. So each computer is given a time token in which they can make use of the network. All right, now that would mean that the speed of the network is going to be very dependent upon this token time that is actually given to them. All right. And it could also mean that if this computer, for example, needs to do some heavy data transfer, all right, and the other computers do not, then it's going to be hampered, all right, because the token time might be equally divided, all right, and it will have to wait its turn for it to start again, to start the communication again. Another problem with this token ring network is that if one node collapses, then essentially the entire network would collapse. All right, and the network administrator would have to go through each and every individual node on the ring topology in order to understand which node has actually fallen. It's also a bit complicated to set up in order to introduce yet new nodes in the token. All right. Obviously, you would need to wire the computer, the new computer, so that it will actually be able to sort of like slot in between two existing nodes over here. There are obviously other variations. You can have, for instance, a dual ring topology. So you'd have one ring maybe going around in one direction and another ring going around in the other direction, again, in order to save with redundancy. All right. So if one ring falls, you'll have the other ring available to you. All right. But again, it requires that the data that is traveling through the network travel through each individual host until it reaches its destination, essentially. Okay? Any questions with regards to this form of topology?
How would the? Not sure if you said that. Sorry.
No, it's okay. Go ahead.
How would a computer detect that it has the ring? I'm not sure if you explained this already, because at one point I blanked out. But how does a computer detect that it has the ring or is about to have the ring?
No. So
Or
essentially,
the token? Sorry, not the ring. Sorry, the token.
the token. All right. So that would probably be a protocol that would be shared across the entire network. All right. So essentially, you would again you would set up each computer. All right, in order to say you are going to make use of this time slot. You're going to make use of this time slot. You're going to make use of this time slot, and you're going to make use of this time slot. So this has to be manually done for each node on the token ring.
Okay.
All right. So it's not that, as you can see, the more you start adding, the more computers you start adding to this system, the more complicated it starts to become.
And I guess the longer that you have to wait for the token.
Yes, but then usually what happens is that you start dividing the token into smaller and smaller chunks, so that the wait time is less. But then if the wait time is less, uh, the amount of data that you can send at any given point in time is also less. So it's a bit of a give and take situation, if you will. In fact, these kinds of topologies, the ring network topology as well as the bus topology, are not particularly that useful. All right, when it comes to high data transfer. The only way that this sort of bus topology becomes suitable for high data transfer is if the backbone, all right, is using something like a fiber optic technology, for example. And over here, instead of computers, you would have buildings, like and then making use of the access, the access distribution and core network hierarchy that we talked about. All right, the access distribution core network that we talked about. So essentially, the core network will actually be a fiber optic backbone, if you will. All right.
Okay. Thank you.
In that case, but usually these types of topologies tend not to be that that suitable, all right, for large volume data transfer. As we said, also, it will also require that the data travels through each and every individual node, and if there's a failure in one of these nodes, then essentially what that means is that the ring topology fails, essentially. Okay. Yes.
Could I ask, can you give an example of when you would use ring topology? Because it seems like it has a lot of problems.
It does. However, the ring topology is usually quite useful when it comes to hybrid systems, as we're going to be seeing in a moment.
Okay. All right.
Okay.
Thanks.
On its own, it might be problematic. But if you're going to be creating a more a topology which makes use of the one advantage over the other, then or makes use of different topologies merged together, then it can become quite useful. All right. This would be problematic. All right, the ring topology would be quite problematic if you are trying to wire up an office, if you will. All right, an individual office. However, all right, if you had to imagine these computers or these icons that are being shown over here as computers as being buildings, then the story becomes a bit different. You're not going to be introducing new buildings that regularly as you would introduce new computers. You understand? I mean, it's quite easy to introduce a new computer.
Yes, but then your data packet would have to travel through several buildings before it reaches.
True, but if these were servers, you know,
Hmm.
which and your servers are connected in a ring together, then essentially what you could have is you you would have high speed data communication being flowed through those servers. You might also have redundancies. As I said, you might have multiple rings. All
Okay.
right, in order to help with communication. All right, so it wouldn't mean that if one node finishes is unplugged and the entire system fails. You might have redundancy in that system as well. You know,
Okay.
Obviously,
Thank you.
when it comes to networks, sometimes we tend to look at networks in terms of the networks that we are familiar with, and we're usually familiar with the local area network that we might have set up in our homes, etc., etc., etc. But sometimes it's good to think about different situations, um, even with in terms of larger scale networks, right? So certain technologies might not really make much sense on the small scale, but make a lot of sense in the larger scale, and vice versa. There might be certain technologies that don't work very well in the large scale, all right, that work very well on the large scale, but don't really work well on the small scale. So sometimes you need to identify what the pros and cons are for that particular system, and then adapt accordingly.
Okay. Thank you.
Okay. Any questions? Other questions? Okay. Cool. So as I was referring to. Yes. So another type of topology, which you're probably more familiar with, is the star topology. All right. Now, the star topology essentially will have each and every one of the component or the nodes of that particular network linked together by a central node. All right. A switch, a router, all right, a hub, all right, gateway, whatever it is. All right. Essentially, all communication, all right, that is going from one computer to the next, all right, needs to pass through this central node. Now, the advantage of the star topology over the other two topologies that we've seen is that essentially direct communication can happen between one computer and any other computer on that network. All right, but it's always going via the central node. All right. So essentially, if you want to communicate between one computer and the next, all right, you just need to plug in, or you need to have access to that central node, and that device will be able to find the path to that particular computer. Notice that the other computers, all right, would not be privy, all right, to that message that has been sent, essentially, because it never was routed to them. All right, that data was never routed to them. It was routed directly from node to node. All right. Obviously, there are a number of issues that exist, all right, with this particular topology as well. What do you think they could be?
Can you repeat the question, sir, please?
Well, as like we've seen with previous topologies, there are some disadvantages. Yes, obviously, like there were advantages as well. We just talked about the advantages of the star topology.
Mhm.
What disadvantages can you see?
Well, if the central node, if the switch is fails, there doesn't seem to be any failovers
Yes,
or redundancy. Sorry.
exactly, and that is something that I would imagine Bridget also mentioned as well. Yes, the dependency on the central node. Very good. So it's the speed, all right, as well as the dependency on the central node. So if you have a slow device here, all right, then the speed of the communication that you would have on your device would depend entirely on your central node. All right. So if you have a slower router, for example, then the data traveling from one computer to the next will be dependent on that slower node. In fact, when it comes to network speed, all right, we usually determine that through the speed of the slowest node. Okay, the slowest node is basically going to determine the maximum speed of that particular network because it's going to be the bottleneck. Okay. If it weren't the case that the central node does not affect the overall speed of the network, then a router that came out 20 years ago, all right, would have the same speed as a router that came out yesterday. You know, you understand this notion when in actual fact it's not. That's not really the case. Any questions?
No, this is understood. Thank you.
Okay. Another type of topology is the tree topology. Now, the tree topology is very similar to the hierarchy that we sort of like were discussing earlier. All right, the tree topology essentially is a topology whereby network access is sort of like distributed upon many different levels of network access. So essentially, it's like having the core layer, the distribution layer, and the access layer. All right, kind of like what we see over here. Okay, that is a tree topology. In this case, you could also think of this as a star to star topology. Why? Because if you look at this node over here is acting like a star topology between these three nodes. And this node over here is acting like a star topology for these nodes down here. Okay, so a tree topology, all right, allows one to be able to break up, if you will, networks, all right, into sub networks, all right, in order to help in distributing access across your system, essentially. Okay. Essentially, the cool thing about the tree topology is that just like with the bus system, you still have point-to-point communication. So I still can communicate from one node to any other node on the network. Uh, However, there are certain nodes in this case which are going to be more critical than others in terms of communication. So, for instance, if this computer here gets knocked out, all right, then essentially the communication of the rest of the network essentially still continues. However, there are certain nodes which are actually more critical than others. Okay. Is this clear?
Yeah, it essentially has similar disadvantages to star topology.
In this case, yes. In this case, this particular tree topology is also set up in a sort of like star manner. All right. A tree topology does not necessarily need to be set up in a star topology manner. Just saying. All right. So this, for example, this access here could be replaced with, say, a bus topology or a ring topology over here. You know, doesn't necessarily have to be an access topology either. All right, a star topology either. All right, it just makes more sense visually in order to represent it as a sort of like star to star topology. Okay.
All right, thank you.
And yes, another form of topology that exists is known as the full mesh topology and the partial mesh topology. All right, let's take a look at the full mesh topology. What's the difference between the full mesh and the partial mesh? What do you think?
Some of them are actually like with the partial with full mesh. Each device is in some way, each node is in some way connected to another node in the network each time.
The level of connection.
While partial mesh, it isn't the case.
In a full mesh, right, each node is directly connected to each and every other node. Okay. Whereas in a partial mesh, that's not necessarily the case, as sort of Floyd indicated earlier. So why would somebody go for one system and why would somebody go for the other system? So with a full mesh topology, essentially the main advantage of this is that there is a direct link between every node to every other node. All right. So therefore, the full bandwidth between of the connection can be used between communications between those two nodes. Is that clear?
Yes.
Now, the problem with a full mesh topology, as you can imagine, is that every time you add a new node, all right, wiring and setting this up becomes more and more complex. All right. So in this case over here we have six nodes. We have 6 nodes. So that basically means that every node needs to have 5 connections. All right. So that it can connect to each and every other node. Okay. And that is the same for each and every one of these. And every time that you're going to run a connection between one node and the other, it can actually end up being very, very, very expensive. Okay? So, but it has the advantage of having a direct connection between each node and each and every other node. Okay? What happens if one of these lines falls or becomes broken or whatever? Then essentially that becomes a partial mesh topology. A partial mesh topology is one whereby not all of the connections have been made, but some redundant connections have been made, so that if communication needs to happen between one node and the next, it might not necessarily use a direct route, it might use an indirect route. So, for example, if this node wants to communicate with this node here, all right, it can use several different paths. All right. In the full mesh topology, it will just communicate with it directly. In this case, what it could do is it can communicate with it via this route here, or this route here, or this route here, or this route here. All right. So depending on what routes are actually available to it at any given point in time, packets might actually travel around the topology, all right, to arrive at that destination in order to make better use of the system. If you think about it, this is basically what probably the transport minister would prefer that each and every locality would be like, all right, with a direct route from one village to the next, if you will. But this is obviously not possible to do, all right, in terms of a road network. Our road networks are more somewhat like this, if you will. But we know that if one road is congested, what we tend to do is find an alternative route. So essentially, that is one of the main advantages of a partial network. All right, is that you have some redundancy. All right, which is also afforded to you by the full mesh topology. All right. However, it's not as comprehensive as the full mesh topology, obviously, but it also makes the network a lot cheaper to run, all right, and a lot cheaper to maintain. Does this make sense?
Yeah, that can also be a case of security, perhaps.
What do you mean?
For example, if you take the top node
In which case? Sorry.
in the partial mesh,
Yes.
that can only be reachable by two other nodes, technically speaking.
Yes.
That would make connections to that node a bit more limited
It could
because they
be.
can.
It could be because they are limited by these connections over here. But then it depends on obviously how these two connections are set up.
As that, so technically speaking, any connection that needs to go to the top node needs to go through these two. So wouldn't it make it?
You could look at it in that way, yes. To be fair, you could also set it up over here. However, you would be able you would set it up in a way that you would have to specify what type of connection each and every one of these nodes would have with each and every one of the other nodes. You know, so if I wanted to have a similar sort of like security protocol that you're sort of like mentioning over here, All right. What you're saying is that you would need to set up these two nodes with rules as to how you can access this particular node.
Yes.
Where in this case over here, you would need to set up rules for how each and every other node can communicate with it, rather than have to set up these two nodes. You'd set up this individual node in this case, if you know what I mean.
All right. Okay.
Obviously, this full mesh topology is faster than this partial mesh topology. But as you can imagine, this full mesh topology is significantly more expensive, all right, than this partial mesh topology, all right. This full mesh topology also has a high degree of redundancy implemented, all right, because if any one of these connections breaks down, then essentially, all right, it becomes a partial mesh topology, all right, and therefore you would be able to still pass around messages. In fact, this kind of topology is used when connections are highly necessary to not fail. All right, when you need secure lines, all right, and you need to ensure communication. All right, so if you think about, for instance, the way that secure systems would be connected with each other. I don't know, the Pentagon with the White House, with CIA and the FBI, and so on and so forth. They would probably have something close to a full mesh. You know, close to, not necessarily a full mesh. All right, but when communication is absolutely 100% vital, they would set up a full mesh topology. Was this clear?
Yes. Okay, sir.
Okay. Mana. So the next type of topology that we have is the hybrid topologies. As we can see, we can have multiple types of topologies connected to each other, all right, in order to make yet more complicated types of topology. So over here, for example, we have the star ring topology, where we have a number of star networks connected together via a ring topology. Over here, we have the star mesh topology. So different star networks connect together in a mesh network. Over here, we have the ring-ring topology. So this ring is connected to this ring, which is connected to this ring, which can be connected to this ring. So essentially, this is a very convoluted ring upon ring upon ring topology, if you think about it. All right, this is yet another ring, if you will. All right. Complicated set up, all right, in order to ensure that your connections are still, or your messages or your data is still going to traverse the network, if you will. All right. Obviously, with a system such as this, certain nodes could knock out other nodes within your network. All right. So, for example, if this node, for example, gets knocked out, then essentially these two nodes will no longer be functioning. The rest would function for the simple reason that they are connected to yet other rings. All right. So it depends entirely on the overall structure. So, for example, if this node gets knocked out, all right, then these two nodes will no longer work. But as a result, so essentially, you start to be able to identify where the problem could be as well in a much linear fashion. All right. Obviously, these are just examples of different hybrid technologies. All right. So over here, we also have, for example, star bus topology. This is basically what most campus style networks um, uh, are actually designed like. All right, and then obviously over here you have a star topology, right, which is predominantly something like what we've seen with regards to the tree topology. So this is very similar to a tree topology if you had to think about it. Okay. So that is essentially those different types of topologies that one can actually look up. And obviously, there are other forms of hybrid systems that exist as well. All right, so it's not just these hybrid systems that I'm showing you over here. Okay, there are others that will obviously exist, which are obviously a bit more convoluted, that can actually be a bit more complicated in order to understand. All right, but they do exist. Are there any questions with regards to what we've just seen? All right. So, essentially, in these set of slides, we've gone over the history of data communications and we've taken a look at certain definitions. We've also looked at different channel types, all right, and different characteristics. And we've also looked at different network topologies and their attributes so that we'll understand a bit briefly as to the different types of networks that we can actually come across ourselves. All right. For more information, I would highly suggest that you take a look at these links, all right, over here in order to be able to understand a little bit more about what we've talked about, all right. And we can now move on to the other topic. So, if you remember, last week I have also given you that little piece of homework in order for you to watch the first part of the video of networks and internet, all right? But basically, in order to understand how communication happens. Have you actually seen that video by any chance?
Yes, I saw it.
Yes.
Maybe.
Cool. All right.
Yeah, me too.
No.
Yes, it is a bit wacky. Yes.
A
There
bit.
were
And this is a bit dated, this as well, in terms of its graphics, at least. However, the principles behind it are very, very fundamental, as in they still hold water today. We still make use of similar technologies, all right, nowadays, just using faster and faster devices and faster means of communication, you know, so even though it's a bit wacky, and even though graphics are a bit on the dated side, the principles are very, 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 very similar to the way data communication happens nowadays. All right. So cool. I don't know if you had any questions with regards to what you saw in that particular video that you would like me to explain.
Perhaps the first part, because I did not understand how when we click on a link, okay, it starts a flow of information which is then handled by IP
All right.
to be packaged into several packets according to the size of the info, but
So essentially, um, uh, whenever you have an application that wants to send a data packet to another computer on the network, all right, essentially, what happens is that application needs to package it up, all right, in order to be actually sent to the other individual. We're actually going to be talking about that when we actually talk about the OSI layers and the TCP/IP layers. Essentially, in a nutshell, all right. What happens is that when an application needs to communicate with another remote application, the data that needs to be sent needs to be split down and packaged in a way that makes it sendable over the network. Okay? So, let me give you an example. If I clicked on a link, all right, or to download a file, for example, from a website, then essentially my web browser somehow needs to tell that web server that I want to download that file, all right, and then it will send me the file. Okay, so essentially that's what's going on underneath. So each application, so essentially when we talk about the OSI layers and the TCP/IP layers, all right, what happens is that at each layer, all right, your data gets packaged with more and more information that allows it to send that data across the network. All right, so essentially, you would go through each layer using different protocols, if you will. Okay, in order to be able to send the data in a very similar way to how, for instance, if you had to write a letter, okay, what do? You write the message on the piece of paper. So that is your data, if you will. Correct?
Yes. Okay.
All right. Now, you don't just send the piece of paper. What do?
You mail it, as in you put it in a mailbox.
But before you
Sort
put it in
of.
a mailbox, what do?
In a letter, in an envelope.
You put it in an envelope. So essentially, the process of putting it in an envelope is essentially enveloping it, all right, with another sort of like layer. So you've gone through the protocol, if you will, of placing your data, your message, all right, into an envelope, all right. Now that envelope, on it, there's going to be certain pieces of information, which is what? The address that you're going to be sending it to, as well as the stamp that you're going to be using in order to pay for the delivery. Correct? That is essentially what you do. Okay? But so that is once, but by putting it into the letter, into the envelope, okay, and putting a stamp on it, it doesn't mean that it's magically going to go to its destination. You then need to put it into a letterbox. All right, so that is yet another container, if you will. That in turn needs to be taken to the sorting office. The stamp needs to be checked and stamped, and so on and so forth. So as you can see, each and every one of these steps, all right, needs to be done before, all right, that letter can then be sent on its way, all right, to wherever its destination needs to be. Okay. In a very similar way, the same things are being applied, all right, by your computer as it goes through each and every different one of these layers, which we're going to be discussing in a future lecture. So I'm not going to bore you with it today, all right. It is adding that little bit of additional information to make sure, all right, that data can actually be sent to the destination. All right. So essentially, you need to say, all right, the data that I'm sending, all right, is split up into, say, 5 chunks. This is chunk number 1, for example. So that is one layer. The second layer will say, all right, this this chunk is applied this particular piece of data can be read by this particular software application. So that is sort of like another layer. If you think about it, each and every piece of data that you have is sort of like wrapped upon wrapped upon wrapped upon wrapped. Think of any
Like a
item.
Russian doll as well.
No, think it's like an Amazon delivered product. Whenever you buy something from Amazon, the actual device or whatever you bought from Amazon, that's usually wrapped in something else, which in turn is wrapped in something else. In order to aid delivery. Okay, that is essentially the process, and sometimes you might have certain wrappers, all right, which haven't come from Amazon, for example, but are actually attached by the courier, for example, all right, that you might have used, all right, and every one of those layers is basically a layer that is surrounding the actual item that you've purchased in this case. All right, and a very similar thing happens to data that is actually being sent across the network. So essentially, the data is at the center. All right, that gets wrapped with new layers. All right, as it goes with new wrappers, if you will, as it goes down the layers of the TCP/IP model. All right, it travels across the network, which in turn decompress it or extract it from those layers until you eventually read the data. So it is on the way down, as you're sending, you're wrapping it. All right, and following different steps and different protocols and different procedures in order to be able to send it. And when you are unwrapping it, you are doing the inverse essentially. Does that make sense? Does that answer the
Yes.
question?
Yeah, it makes much more sense. Thank you.
Okay. So, yes, it is. So when it says it's like your own personal mail room, that is essentially what it means. Okay.
Okay, alright, alright. Thank you.
Okay. So, with the final few minutes that we have together, all right, last 12 minutes that we have together, all right, what I wanted to start off is by talking a little bit more about networks. All right, as we saw, the idea of a computer network is essentially a bunch of computers connected together, all right, in some way, shape, or form using different topologies. All right, and each computer or each device on the network we can call a node. All right, and each node has its own unique address. All right, so what we're going to be looking at is how these different networks work, all right, and how they can actually be classified, all right. Now, there are four different sort of like types of classification that we can talk about. There's the connection, all right, how the devices are actually connected from one to the other, all right. The other is going to be scale. The other is going to be with respect to network architecture and with respect to network topology. I know we've already sort of like skimmed over some of these elements, but we're going to delve a little bit deeper into these notions. All right. So the first notion that we're going to be defining is the idea of the connection method. All right. So essentially, when we're talking about connection method, we're talking about what hardware, all right, or what software technology is used in order to connect these devices together. Now, these can range from a number of different ways, all right. You could have wired technologies, all right, or wireless technologies. So wired technologies, with wired technologies, we're talking about the idea of fiber optic, the idea of Ethernet, the idea of coaxial cabling, or I don't know. Um, you could also make use of cabling. You could use DSL lines. You could use telephone lines. You could use. There are a number of different wired wired options that one can use in order to connect different nodes on a network together. In a very similar fashion, you also have the wireless networks. So we're talking Bluetooth, Wi-Fi, infrared, all right, near contact field, all right. These are all different types of wireless communications that can actually happen between different devices. Now, obviously, wired and wireless technologies have their advantages as well as their disadvantages, like any other type of technology that you care to think of. Okay, so let's start and take a look at the wired cable types of connection. All right, and we'll start off with the coaxial cable. Now, the coaxial cable, all right, comes in various different formats. All right, there is the tin net cable, all right, or the 10 base 2 cable, or the thick net cable, the 10 base 5 cable. Essentially, the main difference between one and the other is the diameter of the cable. All right, the thin net cable, as the name implies, it is a thinner cable than the 10 base 5 cable. However, being thinner means that it is not. It does not have um, as long as a range as one could have with a thick net cable. All right. In fact, the thin net cable has a range of around 185 meters, and as I mentioned, it is usually used in something like a small bus network. All right. You probably have seen this type of connection in the past. All right. For those of you who have Melita as their internet service provider, all right, would probably recognize this cable straight away. Essentially, you have a coaxial cable being fed into your modem, all right? Essentially, the cable that you're using for your internet connection is a thin net coaxial cable. All right. Essentially, the coaxial cable is made up of a central copper core. All right, which is then surrounded, all right, by a plastic protective layer. It is in turn shielded. Okay, so it has this sort of like wire mesh around it that stops it from having interference on it, and over the top of that you will have yet another protective plastic layer. Okay, that is essentially what a typical coaxial cable looks like. Obviously, when it comes to the larger coaxial cable, then it is actually a lot more thicker and obviously a lot more resistant to to weather, to moisture, and that kind of stuff. So essentially, this thin net coaxial cable, that is probably the cable that is used in order to feed the internet connection, if you will, into your home. Whereas the thick nets, the thick coaxial cable, that is what is actually being used on the outside in order to connect your home to their distribution boxes. Okay, so this is one way of actually connecting different nodes with each other. Another advantage of the thin cable over the thicker cable is obviously the thinner cable bends more easily than the thicker cable. In fact, usually when it comes to passing any form of cable, you would require to pass it through what are known as easy bends in order not to break the wire, the internal copper core, because otherwise you'd break the connection essentially. Okay, so that's your coaxial cable. Yes. Not usually. No. The speed. Well, yes, to a certain degree, yes. The longer the wire is, the more interference or the more attenuation you're actually going to get. So essentially, it becomes slower and slower and slower the longer the wire becomes. So that, yes, that is going to uh, be the case. The yes. But the thickness would make the attenuation less pronounced, if you will. All right. So you would start obviously the thicker the cable, the more bandwidth you can actually you can actually hold. All right. So to a certain degree, um, um, yes, speed is going to be limited by the thickness of the diameter of the cable, right? Because at the end of the day, the sheer number of electrons that are actually passing through the cable is going to be limited. You know, think of it in this way: if you have a a small pipe or a large pipe, you know, the amount of water that can actually flow through that pipe is actually going to be determined by the diameter of it. So yes, that is actually going to be the case. However, having said this, the coaxial cable tends to allow quite large quantities of data to pass through it. It's quite fast. All right, for the simple reason that the copper core is relatively large, if you know what I mean. I mean, even the thin net cable is um, uh, is quite hefty as a cable, if you know what I mean. And it was in you're going to have quite a good flow through it. I mean, if you use that kind of cabling in order to wire your house for electricity, for example, you'd be able to wire up electric ovens in every room, if you know what I mean. You know, to put the sheer amount of data, power that it can that it can handle is quite substantial. You know, but the longer the cable gets, the more attenuation you actually get. I don't know if that answered your question. All right. Okay, so when it comes to these connectors, to these cables, essentially they make use of what is known as a BNC connection, all right, or Bay One Neil Conselman connector, and they can follow in one of these three types of connectors. All right, you have the T connector. All right, you have the grounded connector where you have this flexible sort of like wire that you can then use in order to ground the actual cable, or you have this open connector so that you'll be able to plug it in into yet another um, uh, into yet another um, network connector. Sometimes they're also threaded, all right, in order to help secure the connection as well. Okay, um, um, and these are basically what they look like. All right, obviously, you can see the difference between one and the other. All right, the thicknet is actually way, way, way more substantial. All right, over the thin net. All right. However, most of the time, all right, in networks, all right, that you're probably used to, you use the 10 base T network cable, essentially what we commonly know as the Ethernet connection. All right, essentially, it uses what is known as a twisted pair of 4 sets of twisted pair cables that allow us to be able to transmit data packets over the network. Yes, in fact, a Cat5 cable, all right, is one which makes use of this of this twisted pair cable, essentially. Cat5 is, essentially is um, one standard that is used. Obviously, there are many various different standards from Cat 1 all the way up to Cat 8. All right, essentially. The idea generally behind these coaxial cables, first and foremost, is to create these backbones, if you will, all right, of bus networks, like so, all right, where you have multiple computers connected to that bus, all right, where you'd have the connectors, the grounded connectors at one end, all right, so, of the cable, and an open end at the other, all right, a repeater between two backbones in order to be able to communicate between devices like so. All right, so let's move on to the twisted pair. All right, so gives you PTSD. Uh, I understand what you mean by crimping these cables. In the past, I've actually wired my entire house with them. I actually had to put in wall-mounted units throughout my house. I had to put in
Ah,
about 50 of them.
whoa.
So
It's easier to put in wall mounts and then plug in a wire than actually doing the twisting and everything with the crimper, with the manual crimper and the wire.
yes,
Yeah, but it's still annoying.
it's still but the ones that I had were um were two less um uh, were two less sockets that I could actually use. They were all Cat 6A connectors that I did around the house. I was using a shielded cable. Essentially, what a shielded cable is a cable just like this. So you'd have 4 sets of twisted pairs of cables, but around each pair you actually had foil. All right, in order to shield them from one from the next.
Or
Um,
or
which
you can have a rubber cross in between.
and I,
Spreading
I I also had the cross as well.
on
So
them
it
up.
so it was so it was the cross and it was the shielding. Um, reason is because I have an old house, so therefore I have to, I had to make sure that once I'm going to do the cables, I'm going to do them right. For the first time round, and I'm not going to do it again. So yes. So essentially, for those of you who are not familiar, is that in this with these cables, essentially what you could imagine is that you have these 4 different pairs. Each pair would have its own foil wrapping around it in order to shield it from any crosstalk that might happen from other cables that you might be passing around around the place, or etc, etc, etc. And then, in order to also help with the communication, is that along the cable itself you would have sort of like a plastic cross, all right? Where if you had to imagine in each sort of like segment of the wire, so imagine you have this is your wire, all right? So this is the outer plastic, if you will. You have a cross in the middle, and then each corner you would have one of these shielded pairs coming out. I had the whole lot. Essentially, that would have been, all right, a shielded twisted pair Cat6a cable in my case. All right, but typically, all right, these kinds of cables come in two forms. All right, you have the unshielded and the shielded. The unshielded, as you can imagine, usually are a lot more flexible. All right, and they're usually more popular with regards to patch leads. All right, so the leads, all right, that you use in order to connect your computer, all right, with your router, for example. All right, that is a patch lead. Okay, so if I had to show you, give me a moment. So, for example, this here, right, as you can see, I have two RJ45 connectors here, all right? That is a patch lead. In my case, I went a bit overboard, and these are also shielded, but you get the idea, okay? So essentially, the idea behind it is that you use these kinds of cables, all right, in order to plug in into an interface where you use these adjacent pairs together, all right, to form the basically the connectors that you might see over here. Right, there are 8 connectors over here, so that you will allow for communication between devices. Most devices, most home networks that you might, or most devices that you'd see that can actually be connected using a cable, make use of this RJ45 cable connector, which essentially is connected to a twisted pair cable. Now, essentially, the reason why they are twisted is so that they help eliminate interference. If they're shielded, they help eliminate interference even more. And the tighter they are twisted around each other, the higher the transmission rate. But obviously, the more expensive the cable is actually going to be. Okay. Um, in fact, when it comes to twisted pair cables, all right, the EIA and the TIA, all right, the Electronics Industry Association and Telecommunication Industry Association, establish the standards for the categories of such wires. All right, and as I said, they range from a number of different categories. They start from Cat 1, Cat 2, Cat 3, Cat 4, Cat 5, Cat 6, all right, and so on and so forth. Okay, Cat 1 is essentially the telephone wire, the old telephone wire, which could only accept voice across it. Okay, Cat 2 was the first one that allowed for data to be transferred, all right, and at a rate of up to 4 megabits per second. Megabits, not megabytes, all right, bits. All right. But this was usually used on a token ring network, on the older token ring networks, if you will. Cat3 allows data up to 10 megabits per second, all right, at a frequency of 16 megahertz, all right. Cat4 allowed for 20 megabits per second, again, or 16 megabits per second for token ring at 20 megahertz per second. Cat5 allowed data of up to 100 megabits per second at 100 hertz. Cat5e, or Enterprise Edition, all right, was 100 megabits per second, or 1 gigabit per second, or gigabit connection, all right, at 100 hertz per second. All right, Cat6 amped that up to 250 megahertz, so the same speed as Cat5e, all right, and Cat5, Cat6a allowed for the same gigabit connection. 10, actually, Cat6a allowed for 10 gigabit connection at 500 hertz. Cat7 allowed for 10 gigabit connection at 600 hertz, and Cat7a allowed for 1 megahertz. All right, along that connection. So obviously, depending on the type of cable that you have, you're obviously going to get different speeds. All right, and different bandwidths. All right, on those cables. Is that clear, guys?
Yes.
Yep.
Okay. All right, guys, we're going to stop here for today. All right, I know we overran a little bit, but hopefully it was a bit worth it. We will continue from here on out in our next lecture. Okay. Thank you very much for listening. Hope you have a good night, and I will see you guys in our next lesson.
Have a nice evening, sir. Thank you.
Thank you.
All right. Thank you, sir.
Thank you, sir.
Bye bye. Bye bye.